No, because there's all sorts of anecdotal stuff from ancient times.
You know, go down all sorts
Building
of
pyramids and all that kind of stuff.
Yeah.
But you know.
Yeah, I thought that one about the Nancy UFO. I got a lot of people come. Where can I find? What's it called?
I'd never seen that before.
No,
No. Did it ever fly?
well, there's one. This is the. I should have put the other one up. There's one with a U.S. Army truck, like with the white star on the side.
Yeah.
Towing the fucking thing.
Really?
I was looking for it, going, oh, I know it's out there somewhere. On this one where the Nazis were fueling it up.
You know, Avro built
An air car thing.
yeah,
too.
type of thing. You know, it's a bit wonky, but okay, don't know until you try, right?
Yeah.
So
How was your trip up north?
good. It was good. Yeah. Some clear skies. Managed to get some observing in, and yeah, it was good. How's your summer coming along?
Up and down. I'm trying to redo the sidewalk in front of my house. I have an exposed aggregate sidewalk I did about 15 years ago, and a few of the panels are really chipped bad, and that, so I hammered that all up. But geez, working in this heat, you know.
Oh, with a sledgehammer? Yeah, yay.
Yeah. Oh, it's just, what do you do with that? But tomorrow's supposed to be better. So
Yes, today was supposed to be the hot day.
I'm hoping I can pour this. I have a video or a cement mixer, so I'm hoping tomorrow pour the new top lift and then do it all.
You got hammered at all by that lovely weather we had on Wednesday?
A bit. I haven't checked my truck. It was parked outside. It was unemployed, but the piece of shit anyhow. But yeah, a lot of the plants got beat up pretty bad.
Yeah.
How about you?
Oh, no, we dodged a bullet. Yeah, had 118 millimeters in the city.
Yeah.
I had 15. The cells were really dense, but they were compact and they were moving quickly. And the one that hit Ottawa, just barely grazed us on the south edge of it.
Yeah, we got a lot of rain. I live up on a hill and I have a gravel driveway, and it's just all rutted again.
Ah, jeez.
This is gonna have to break it out. And our ditch had water in it. I'm on the top of the hill and our ditch had water in it.
Yeah, that's amazing. No, we didn't. So we had a lot of rain, but it was, like I said, it was 15 millimeters came down in the span of about an hour and a half. Then it was gone. We had the wind and that, but we didn't have the power outages, which is amazing because out in
The
the
wires kept clicking on it.
Really?
I was like, oh, am I gonna have to get the generator out?
Yeah, well, I got a battery backup that powers about half the circuits in the house and stuff like that.
Yeah.
I saw some flickering a couple of times there, but like it switches over so fast that like it doesn't even foul up your computer.
Yeah, with the lights kept on and off.
Oh yeah.
I have a 240 volt 30 amp generator panel, and I have this big portable generator, like a 15 horsepower plug in the side, but starting it, it's a pull.
You good?
No, yeah, we don't have a light on these.
A laser?
No, a light to illuminate my
Well, normally we turn this big one on here that highlights everyone's bald spot there, so you can see on the podium.
That's why I have my filter on, right?
No, we told him to put it on because he was dazzling us.
Yeah, it was just saturating the sensors. Not enough like for the when it comes to spotting, yeah, better yeah, content. I think the content's only for value. Yeah, that's right. Just put in that, you know, yeah, when it comes to state, I did the initial evaluation, I was very generous. I said, let's get back and get that, better than that. So, the content's
Well, I was having a conversation with the real estate agent. We're not trying to sell it. Yeah, no, the other reason. Value of authority. He's gonna tell everyone to sit down.
Yeah.
That's right. That's being so rowdy. Hi. How are you doing?
Oh, that's your signal. All right. Okay, if I can get the house lights on, I think we are good to go. Well, welcome everybody to the July meeting of the Ottawa Centre RASC. I'm your host, Paul Coniger, and I'd like to extend welcome to all our visitors here and other members from the RASC tuning in from across this lovely land of ours. See if I can get our gadget to work. There we go. Just a reminder that we are doing this on Zoom, so we are recording the webinar. And you can use, for those on Zoom, you can use the Q&A function to ask a question of a speaker. Excuse me. And chat box, or just a reminder that chat box comments can be seen by everybody. Also, the raise your hand functionality in Zoom is disabled. All right, the Ottawa Centre acknowledges the trust placed in us by our First Nations with their ancestral lands and skies. And here is tonight's program. And I won't waste too much time going through it because you're all here to see it. All right. There we go. So 31 new members already in 2026. So welcome those. Anybody, any new members here tonight? Oh, okay. Well, welcome to our show. I hope you enjoy your time here, and I think you'll find it interesting. All right, we have two members in the news. Philip Danko, unfortunately, is no longer with us, but his 25-inch scope is now under the auspices of the Lennox and Addington RASC and Kingston Center, and that'll be a treat for them. That is a really lovely scope to be observing with. So it was a wonderful donation from Attila for that center. Also, we have Deborah Saravolo. For those of you that have been around forever, you know who I'm talking about. Deborah and Peter Saravolo were longtime members of the Ottawa RASC Center, and the lucky duo that decided to pack up and move out to British Columbia, where they bought a house on top of a mountain so they can do wonderful observing. So Deborah created this picture, this lovely picture of Venus and the moon. And so I thought we should acknowledge her. Deborah, if you're tuning in, that's a beautiful picture. Hope you and Peter are doing well. All right. So without further ado, David Chisholm is here with our Ottawa Lives for July.
Thanks, Paul. Well, let's see what's happening in July. Well, the full moon was just towards the end of June, so the only full moon we have in July is on the 29th of July, and new moon on July the 14th. And our full moon was known by early Indigenous folks as the buck moon. So the male buck deer would begin to grow their new antlers at this time of year. It's also been known as the thunder moon and the hay moon. We have the Delta Acrid's meteor shower, July 28th and 29th, perfectly aligned with the full moon. So probably won't see them very well. And there's about 20 meteors per hour, but it'll be pretty well washed out by the full moon. The days are getting shorter in terms of sunlight as we've passed the longest day of the year. Mercury is not visible, it's rising and setting with the sun this month. Venus is visible in the early evening, and Mars is visible before sunrise. Jupiter is visible in the early evening first half of the month. By the end of the month, it'll be setting in the sunset. Saturn is visible before sunrise. Uranus is also visible before sunrise, and Neptune is visible late evening and through the night. And here is our cartoon. Now, you may not be able to see the words there, but it says adjust azimuth by 1 degree clockwise, wind speed is 4 knots from the northwest. So you can get assistance there from the wildlife. Thank you. Nice one, Dave. All right. Go. All right, so our first talk of the evening comes to us from Simon Hamner. And he's gonna address the question of how did the moon form? There you go, sir.
Okay, remind me which button does what.
So that's forward.
Yeah. Okay. Very good. Okay. Okay. There. Okay, very good. Although the deep sky images and observers on Mars may disparage the moon when it's full, the moon has fascinated humanity since we lived in caves, and maybe before that. Once we realized that the moon was an astronomical as opposed to a theological object, about 400 years ago, think Galileo, mankind has been asking the same fundamental question. How did the moon form? Now, after more than half a century of active space exploration, you would be forgiven for thinking that maybe scientists have come up with an agreement on the origin of our nearest astronomical neighbor. But in 2026, it doesn't seem as though the question is quite as settled to everyone's satisfaction. I see, I did that one wrong. There. Over the past 10 years, from this podium, I've discussed with you the most recent theories of moon formation, specifically in my 2016 and my 2019 presentations that you can find on my website, which is indicated in the upper right there, if interested. However, the question, how did the moon form, is still being asked within the planetary science community, and attempts are still being made to test the proposed models. In fact, a paper in a peer-reviewed scientific journal published earlier this year really made me sit up and pay attention. But more on that later. So with this in mind, plus the media interest in NASA's current and future Artemis program, I thought this would be a good time to take another look at where planetary science is today in 2026 regarding the moon's origin. It doesn't get much more basic than that. Yeah, there we go. Now, it may surprise you, but in order to set the latest ideas on the origin of the moon in context, we have to go all the way back to George Darwin, the son of Charles Darwin of evolution fame. In 1878, George Darwin proposed his fission theory for how the moon formed. Simply put, he proposed that the early Earth spun faster than it does today, for various reasons, and that the faster spin created a bulge on the planet near the surface that eventually broke away and began to orbit the Earth as the moon. He also suggested that the Pacific Ocean between Asia and the Americas represents the scar from which the moon was torn out. It's roughly circular, and it's about the right diameter. And this is what I was taught in primary school many years ago. However, there are at least two fundamental flaws with George Darwin's hypothesis. First one is that the Earth would have had to have spun so fast that its day would only have lasted about 2 hours. And at that speed, the entire planet would probably have flown into bits. Even if the Earth could hold together at that rate of spin, the resulting Earth-Moon system would have had way more angular momentum than it has today. Angular momentum, just think energy associated with something orbiting or spinning. And scientists cannot say where that extra momentum could have gone. The second fundamental flaw is that in the 19th century, no one knew that the Pacific Ocean floor is the product of plate tectonics, or that the ocean floor is younger than about 200 million years. Also, they didn't know that the Earth was about 4.5 billion years ago, and that the moon is roughly as old as the Earth. So we do know these things, and so we know that the Pacific Ocean is way too young for George Darwin's fission theory. Whoop, got it, good. Okay. Now, fast forward to the late 1960s when NASA astronauts landed on the moon, grabbed some rocks, and brought them back home. Chemical analyses of these rocks showed something hitherto unexpected compared to the Earth. Compared to the Earth, the moon's chemistry is strongly depleted. In other words, it's lacking in volatile elements such as sodium, potassium, rubidium, but especially water. I'm not talking about the water at the surface, talk about the water inside, actually in the rocks, in the minerals. Oh, there goes my light. There we go. If the moon really was formed out of the Earth, then this depletion, in especially water, calls for a massive vaporization event. And the question is, what and how? Now, at the same time, planetary scientists were beginning to make quantitative models, calculations, about what might happen if the early Earth was involved in collisions with other bodies left over from the accretionary stage of the solar system construction. A really big collision could just provide just such a vaporization event that they were looking for. Now, building on this, early computer simulations suggested that the moon could have formed by a massive collision between early Earth and a Mars-sized impact of Theia. I'm sure that some of you know about this because I've told you about it. According to this, the classical collisional model, the impact resulted in a massive ejection of debris that formed a ring around the Earth that rapidly coalesced, in other words, accreted, into the moon in about 1,000 to 10,000 years. And you can see that illustrated here with a blow-up of the explosion. Now, in addition, and again, according to the classical collision model, Theia contributed about 70% to the mass of the moon. That's an important number for you to remember. And I'll come back to that in just a few minutes. Now, in addition to coalescing to form the moon, this debris ring was envisaged by the theory as being zoned, kind of like a sandwich, with an inner ring, that's the bright orange thing here, the meat in the sandwich, if you like, of droplets of molten rock, a magma disk, bordered by an atmosphere of vaporized rock. And that's the atmosphere out here where you can stop. And that's vaporized rock, and that's molten rock. Now, while we're on this slide, notice how the circulation within the debris is highly localized within its constituent parts. Here's a representation of convection within the vapor atmosphere, and similarly within the magma disk, but they don't mix between them. In other words, the debris disk is zoned and it stays zoned. The classical debris disk is not well mixed. Remember this, because this will be important in a few minutes too. Now, according to the classical collisional model, over a period of weeks, the part of the debris disk furthest removed from the Earth. In other words, that's this part out here. That's supposed to be the Earth. It's red because it's very hot and probably partially molten. So that part there began to cool and form particles of various sizes that then progressively coalesced or accreted over several hundred years to form the moon until the full debris disk was consumed. But you can see that the debris beginning to coalesce into larger bits and pieces, and eventually all swept up into the moon. Now I need to add just a wee bit of physics here, and that's because of this thing here. That line is called the Roche limit. The Roche limit around the Earth is the radius within which coalescence or accretion of material into a solid body cannot happen. And it cannot happen because the Earth's gravity would tear apart any large accreted body that lies between the Roche limit and the Earth. Hence, the moon must have formed from debris located beyond the Roche limit. In other words, out here and not in there. While debris from the disk, the debris disk material located within the Roche limit simply fell back to Earth. Post-Apollo, this remained the consensus model for the moon formation for about 40 years, until it became apparent that there were a number of problems with it. First problem was that the classical collisional model predicted that the debris disk should form over the Earth's equator. However, the moon's orbit is tilted with respect to the Earth's equator, and that's a physical problem. And secondly, and even more importantly, planetary scientists were able to analyze the samples brought back from the moon by the Apollo program to such high degrees of accuracy and precision that it became very obvious. There's a limit on this, I don't know why, I'm being rational. That there was very obvious there's a chemical problem with the classical collisional model. The mantles, the stuff between the crust on the outside and the iron-rich core on the inside of both the Earth and the moon are chemically indistinguishable. And that's what this specific diagram illustrates. When you plot the chemistry of mantle-derived rocks from the Earth and rocks derived from the moon, so those are the lunar rocks and those are the Earth rocks, they all lie on exactly the same straight line. And for those of you that remember your high school chemistry, that this diagram is illustrating oxygen isotopes normalized to the composition of a standard Earth's ocean water. Simply, when you look at the isotopes of oxygen for both moon rocks and Earth rocks, they are identical to a very high degree of precision. Now, we don't need to go into the details here, but all attempts to try to explain this chemical identity, similarity, failed. They either relied on too much coincidence. Scientists do not like coincidences for anything, or they were simply overly constrained. In other words, there were too many assumptions that had been made instead of observations and measurements. Understandably, it's kind of difficult. And because of the difficulty in explaining the isotope data, many scientists began referring to it as the isotope crisis. But why is this chemical identity so important? What's the problem? Well, here's another plot of the oxygen isotopes. It's pretty easy to read. That dashed horizontal line, that's the composition of the Earth. There's the Earth in that box. Terrestrial fractionation line. Don't worry about what fractionation is. That's Earth data in that box. And along that line, there's the moon data, all lined up with it. Exactly the same value. Don't worry about what the value is. So therefore, they're indistinguishable. The moon rocks are indistinguishable yet again from the terrestrial signature. But look at Mars. A very different array. And then here you've got asteroids, all different kinds from all different parts of the inner solar system. And they lie well away from that Earth-Moon line. Remember, the classical collision, yes, the classical collision model for the origin of the moon predicts that 70% of the mass of the moon comes from the impact of Theia, which of course is a large asteroid from somewhere else in our solar system. But this slide tells us that planetary bodies throughout the inner solar system are chemically quite different from one another and from the Earth, by the way. So it is extremely unlikely that Theia would have had exactly the same isotopic composition as the Earth. If it did, it would be a coincidence, a special case. And again, scientists don't like that as an explanation for anything. So does this mean the end of the collisional hypothesis? No, far from it. Gifted astrophysicists later came up with further computer simulations and found a way to form the moon directly from a collision or a near miss with the Earth without a debris disk forming at all, and without involving too much of the impactor material in the resulting moon either. Now, this slide shows how a model impact might extract vaporized rock just from the Earth. There's the impact. The impact is going off that way, and it's pulling material out from the Earth and leaving some of its own material. The green is material from the Earth. It's green in the diagram. It's not in real nature. The yellow represents material from the impactor. Most of the green material from Earth is placed into orbit, and it then forms the moon. And if I understand correctly, the impactor material, the yellow, what's left of it there, that's that yellow there, and the rest of the green fall back to Earth because they lie within the Roche limit. So they're falling back to the Earth. So you end up with a moon, which is essentially made of Earth material, thereby explaining the chemistries of the Earth and the moon, explaining that they are indistinguishable because they're both made of the same thing, Earth materials. Now, it's a very neat model, but it's just that. It's a model. And it's not the only one that might account for the indistinguishable chemistries of the lunar and terrestrial mantles. Just because you can do this on a computer doesn't mean that's what nature actually did. Perhaps the most popular model at the present time is the one involving a synestia. What is a synestia? It's a donut-shaped cloud, technically called a torus, of vaporized rock. Where does the idea come from and why? Well, it's all down to this mantle mixing issue, the mixing of the compositions of the impactor and the Earth. And the best way to mix the chemistries of the Earth and the impactor mantles is to vaporize both totally, 100%. And the simplest way to do that is with a very high velocity impact, the result of which would look like a donut. In fact, a vast homogeneous cloud of vaporized rock with no zoning that can mix without internal barriers. That's what's represented here with mixing going on. As it cools, condensation in the inner part forms the Earth. So it's cooling and it's shrinking, and the Earth forms there in the middle. And the moon in the outer part forms beyond the Roche limit, which would be somewhere about there. So let's just take a closer look at this mantle mixing issue. Juggle it here. There we go. All right. There. The top row of this cartoon here, in this slide, represents what happens after a classical low velocity impact scenario with a debris disk. The terrestrial and lunar mantles, that's moon, that's Earth. The terrestrial and lunar mantles are not thoroughly mixed with each other, or individually, by the way. So their chemistries will definitely be different. The bottom row here with our synestia model shows that the high velocity scenario with a debris cloud, where the terrestrial and lunar mantles are thoroughly mixed and chemically indistinguishable on all scales, even if their cores are not proportionally similar. However, there are still some aspects of the Earth-Moon system that the synestia model doesn't explain very well. So although scientists like it, and this really is the consensus model for now, it's a consensus model with hesitation. And I am going to my next slide. There we go. Nevertheless, until the beginning of this year, I was under the impression that the synestia was the favored model for formation of the Earth-Moon system, involving a collision between proto-Earth and Theia. However, and unbeknownst to me, for the past decade, there have been rumblings in the scientific literature about another model. One that sounds very much like George Darwin's 19th century fission model, but on steroids. I first heard of this idea last February when I came across a paper that attributed the origin of the moon to something called explosive fission. At the risk of oversimplifying, the author's rationale was that in order to reduce the spin of the early Earth to prevent it from breaking apart and still derive the moon by terrestrial fission, ejection of material to form the moon was going to need an extra energy boost. So the question became, where do we get that extra energy? But before I can address this question, I need to brief you briefly about evolving current ideas regarding the interface between the Earth's mantle and core. And of course, I'm sure you're all aware that there's the core, the liquid outer core, solid inner core, there's the mantle, and the crust is on the outside. This is the geography of the Earth. I'll come back to that in a second. Deep below Africa and the Pacific Ocean are two rock masses, here called Tuzo and Jason, named after two very famous geophysicists, Tuzo Wilson and Jason Morgan, who were really important at the beginning of the formulation of plate tectonics. These rock masses are called large low-velocity provinces, and they are big, thousands of kilometers wide by up to 1,000 kilometers thick. And they're represented here at the core mantle boundary. There's Jason, there's Tuzo. And this is to show you that Africa is hiding under here, under Tuzo, and Jason is down at the bottom of the mantle under the Pacific Ocean. Now, a fundamental tenet of geophysics is that the deeper you go into the mantle of a planet, the density of rocks increases as the pressure increases. And as the density of rocks increases, so the speed at which seismic sound waves travel through rocks also increases. So it came as a great surprise to everyone when these low velocity provinces were identified as zones where the speed of seismic waves is significantly lower than geologists would expect, not higher, lower. What are they? Quite simply, we do not know. However, there are theories, one of which suggests that they might be leftovers from collisions with the proto-Earth at the beginning of the formation of the solar system. And some supporters of the collisional model have asked, could they be pieces of Theia? In other words, maybe we could solve the isotope crisis if this is simply Theia hiding at the base of the Earth's mantle. But notice the emphasis on maybe. We really don't know. So let's not go down that road, or rather down that rabbit hole for now. Here's an animation. Thank you, Chris, it works. To give you a 3D view of these large low-velocity provinces as we see them today in seismic imaging. You can see there's one. And they're pretty big and they're very complicated. We can see them, we don't know what they are. So, let's set aside for the moment the collisional model. Let's go back to the question of where to get that extra energy for this explosive fission model, which is required to run that model without tearing the Earth apart. As recently as 2013, a paper suggested that a nuclear explosion at the core mantle boundary of the Earth might do the trick. Now, before you roll your eyes, there are such things as natural nuclear reactors in the Earth's crust. The one in Gabon is the classical example. But we know very little about the deep mantle in this regard. However, had such an explosion occurred, though it's far from obvious how, it could have allowed for the fission of the moon, or sorry, fission of the Earth to produce the moon with a slower rotating Earth 6-hour day. Whatever. The 2026 paper tries to combine these large, low-velocity provinces and the notion of an explosive fission of the Earth to form the moon. To try and follow it. According to the author's theory, first, the precursors, the seeds, if you like, of these large, low-velocity provinces are assumed, emphasis on that word, are assumed to have nothing to do with the Theia-type collision. And they simply are part of, they're an intrinsic part of the mantle, however that occurred. And secondly, according to the author, the large, low-velocity provinces themselves are again assumed to form from these seeds by a combination of tidal forces driven by the sun and heat emanating from the Earth's core. But it's really unclear how. And third, because heat only escapes from the lowermost mantle very slowly at this time, there was no plate tectonics. The author assumes that it builds up, the heat builds up in these large, low-velocity provinces. Now, at this point, in the explanation, the author switches from talking about heat to talking about energy. And this is where his argument gets very difficult to follow. His idea is that the built-up energy goes critical. If you look at this diagram here, that's supercritical zone, whatever that means, at the base of the mantle. So if that goes supercritical, and that leads to an almighty explosion at the core mantle boundary that expels all this material out beyond the Roche limit, which is then going to go and form the moon, with a chemical signature, of course, that's identical to that of the Earth. Now, it's that last step that I have difficulty following. In other words, where the energy goes critical. In my opinion, it reads rather like, and then a miracle occurred. Don't know if you know this very famous scientific cartoon. Equation, then a miracle occurs, and you go on with the equation. I'm really not sure how this paper got through peer review, but it was included in the scientific journal published by Springer, a reputable international science publishing house. And this is just one of a set of papers over the past decade that seems to be going in this explosive fission direction. So let's just say that I'm perplexed and leave it at that. Okay, what's the take-home message here? Astronomically speaking, the origin of our nearest neighbor, cousin if you like, continues to intrigue us, maybe puzzle us. And as my grandmother used to say, there's more than one way to feed a cat sour cream. There's another way of telling that phrase as well, but it's the family audience. And it appears that the scientific community agrees that there's more than one way to explain the fact that the chemical signature of Earth's interior is indistinguishable from that of the moon. I'm sure you've all heard the old adage, all models are wrong, but some are more useful than others. I'm afraid we'll just have to wait and see how these competing models play out. Meanwhile, as always, thanks for listening.
Simon? Just a quick question. Are there gravimetric anomalies associated with those two supposed masses under just on the outer side of the core?
There are. Do I have the?
Oh, yeah, microphone's there. I may have to turn off.
I guess it won't be on. I'm standing in front of this.
You are, okay. I'll hang on for other questions. Oh,
Again, you're gonna have to repeat the question.
I was just asking Simon if there are gravimetric anomalies associated with those two large masses which are straddling the core. In other words, are there anomalies, higher or lower gravitational field than the average field of the Earth?
There's a very well-known gravity signature, or signature in the gravity field, of both over Africa and over the Pacific. the geophysicists talk about a geoid, and this geoid has high points and low points. And I forget which this way around this is, but I believe that these two high points on the geoid correspond to these. However, we've known about that for a long time. Nobody suspected that there were major low velocity masses down there responsible for it. It was assumed that it was mass distributed all the way through from the crust to the core.
Interesting. Okay. Any other questions? No? All right, Chris, anything online?
Nothing online.
Okay, thank you.
Jim Sophia now, delay the break a bit?
Sorry, what was that?
You go
I didn't catch
Jim
that.
Sophia, and we'll do the break after Jim.
Okay.
Yeah.
Well, thank you very much, Simon. That was intriguing. Interesting to see how those thoughts have evolved over the last few decades. All right. Oh, right, it's a nasty feedback. Okay, yes, just a note here, actually. This was sent out to the club there, but for those interested in the Fred Lossing Observatory and using it, the access code for the front gate was changed on Monday, June the 22nd. So if you haven't read that email or haven't already contacted Rick for the code, you should do so before you head out there, because you'll find that the gate will remain locked with your old code. All right. And you can reach Rick at the hello@ottawa.rasc.ca. All right. So Chris, did you say we want to proceed with the bio break, or I couldn't make that?
No, we're gonna do the.
Gonna do Jim first?
Gonna do astrobits?
Okay, sounds good. All right, Jim is going to present an astrobit segment. He has a very interesting set of observations there that I felt was too long for a standard observation report. So we gave him a bit of license to go into the science of what he's doing.
Thank you
Take it
very
away.
much. Okay, so tonight I'm going to be speaking about the characteristics of solar active region. So what is an active region? Well, an active region is a temporary and localized area of the sun's atmosphere that's characterized by a strong and complex magnetic field, sunspots, flashes, and plasma eruptions of various possible magnitudes. In May, I've imaged two of them, active region 4432 and 4436. By the way, active solar regions are officially numbered by the Space Weather Prediction Center and are assigned consecutively as new groups of sunspots rotate into view or form on the sun. So what we have here is AR 4432, a large magnetically complex active region, along with some big, beautiful proms. Passing clouds and poor seeing interrupted the time-lapse sequence, so it appears somewhat choppy. The equipment and software that I used are listed here to the right. But let's take a close-up of AR 4432. AR 4432 on May 11th was the lead flare producer, responsible for 9 flares, the strongest being a C1.9 flare. While active, however, it has primarily produced minor flares, and I'll tell you why that's so in a couple of minutes. The following day, AR 4432 was showing some decay in intensity and visible sunspot count. And on May 13th, it was at the very edge of the solar northwest horizon and later departed to the far side, no longer visible today. Every day, the sunspots on the sun are counted, and every sunspot group receives a sunspot count, a size estimate, a magnetic classification or configuration, as is sometimes referred to, and a spot classification by space weather specialist. As you can see, the chart reveals that during the first 2 weeks in May, when this active region was visible from Earth, its sunspot count, size, and magnetic classification were recorded. The beta classification, as you could see in green, given the first 9 days, indicates a sunspot group. This is the definition of a beta classification. It indicates a sunspot group that is primarily bipolar, having a positive and negative polarity, with a simple division between the polarities, therefore fairly simple classification and not very complex, which usually results in few flares. However, later on, from May 10th onward, as you can see, this sunspot, this active region was designated beta gamma, which indicates a bipolar sunspot group, but complex enough so that no line can be drawn between sunspots of opposite polarity, a situation of greater complexity coinciding with more flares, which is exactly what happened on May 11th. Also, what this table chart reveals are that the characteristics of an active region change in different ways over time. But what I've learned is the significance of the magnetic classification of sunspots, because it's the magnetic classification that really determines the probability of strong flares. Now, I'm not an expert, but from what I've read, this appears to be due to the complexity of the sunspots and the location and distribution of positive and negative magnetic poles within a region. So just for your information, more than half of the observed sunspot groups receive an alpha or beta classification, fairly simple. Bigger sunspots are more complex and get a beta gamma or beta gamma delta classification. A delta classified sunspot, which are known to produce very powerful flares, have an intense active region where opposite polarity umbra, that's plural for umbra, the darker inner part of the sunspot, share a single penumbra, the lighter surrounding outer part of the sunspot. So in other words, these are two opposite magnetic poles packed tightly together within a single penumbral structure. And this is what can cause very major flares. On to the next active region. This is a photo I took, and the active region that we're looking at is right here. AR 4432, which I just spoke about, was accompanied by another active region, AR 4436, which is what you're looking at right now. And AR 4436 replaced it as the largest region on the solar face. And here is a close-up animation sequence of only 45 minutes, limited because of clouds. It was reported that on May 10th, 2026, the sun fired an M5.7 solar flare from AR 4436, one of the most violent eruptions of the year at that particular point in time, creating a coronal mass ejection at an estimated speed of 650 kilometers a second considered moderate, but fast enough to generate a shock wave in the corona. And this resulted in a moderate radio blackout, disrupting high-frequency communications across Eastern Africa. So I hope you've learned a little bit about solar active regions and some of the characteristics that are responsible for how they behave. Thank you.
Any questions for Jim? Oh, one off the top.
I'm just fascinated by by your presentation. I'm just wondering, has there been any predictive models developed? Which might, Sure.
Thank you very much for the presentation. I enjoyed it very much. Have there been any predictive models developed which might give us an idea if there's something headed our way that could be a real cataclysmic event, similar to something that bypassed Quebec a few years back?
Well, I know that NASA keeps
Okay, if we
track.
go back to your mic.
Yeah. NASA keeps track. The Solar Dynamics Observatory takes continual pictures and moderates, keeps track of how the sun is erupting. And it's only at that point that their instruments can predict whether a solar flare is going to be hitting Earth or not. It's actually quite a surprise because we never really know what active regions are going to form or are on the cusp of forming. But we do know that when a solar flare occurs, we can detect the magnitude and direction.
Thank you.
You're welcome.
Well, thank you very much, Jim.
Very welcome.
That's awesome.
Thank you.
Beautiful photography.
Thank you.
Okay, so we're gonna have a bit of a fire break. Please reassemble here in about 10 minutes or so. Go and have a stretch, go and have a drink of water. We'll be back in 10.
Gotta stay on it. The Attica's been really bad.
Linked to the weather or at all, or?
No, my migraines are, but not my sciatica.
Guarantees.
No, it just acts up once in a while.
Well, they're a couple right now.
I think what it was is my chiropractor was trying to fix my clicking knee and he fixed it all right. It didn't click anymore. And my leg hurt.
I would trade off one for another, right?
Yeah. That was great.
No, it's so.
So whereabouts, were you up on Lake Superior then?
Yeah, Lake Superior and then Georgia Bay as well.
Okay.
Yeah, so
You know where St. Joe's Island is? Near the Sioux?
I've heard of it.
I
Yeah.
would have driven past it on 17.
So where is it past the Sioux?
This side of it,
This side out?
about a half hour.
I've heard of it and I've probably seen it on a map, but I can't visit it. It's weird with respect to the dangers.
That's where my dad's family is from.
Oh, really? Okay. Very cool. That's a neat area.
Yeah,
Yeah,
there's
yeah.
lots around it.
Some interesting geology there too.
Yeah. Well, it's funny because St. Joe's Island, half of it is like northern Ontario. The other half is like southern Ontario. My cousin Gilbert said have the largest maple sugar operation in Ontario. Up there,
Up there.
up there.
Oh, wow.
It's all the one side of the island is all maple and oak trees.
Oh. I've got my audio.
Yeah.
Good access to
Try now.
Just have it.
Turn that on.
What?
Turn the handheld down.
Hello. Just getting in. What's that?
Done.
Turn off the
It's off.
Turn off the podium. Try again.
Try.
No.
I feel like
Yeah.
it's a split in reality.
Turn off the laptop.
Try again? Nope. Jim Thompson, could you try talking, please?
Yeah, sure. Can you hear me?
Zoom
one.
can hear you. Can the audience hear Jim?
Testing. Check one.
Yes. You can hear him. So we'll just move forward with him talking.
Paul, did you hear Jim in the room? Did you hear Jim in the room? Push on. Let's push on with Jim.
All right, I'll go ahead and share my screen. Okay, sharing is not turned on yet, Chris. Okay, thank you. So welcome everyone from the Beach Bum Observatory. Unfortunately, I'm not on the beach because, surprise, surprise, a thunderstorm went through about 30 minutes ago.
The laptop. Turn off the speakers.
Okay, there's somebody's mic we can hear there. Oh, I guess Chris just muted. All right, so welcome every day to my talk called The Plumber's Guide to Telescope Building. I'm sure the first question you're asking yourselves is, well, what the heck is Jim talking about? Well, what I'm talking about is using readily available resources to build a decent quality, fully functional telescope. Specifically, I am talking about using ABS plastic plumbing parts for this purpose. Why ABS plastic? Well, because it is rigid and relatively lightweight, and it is easy to work with, and because it is cheap and readily available in various sizes from your local hardware store. So what does it take to build a decent telescope? This figure illustrates the important features that are required, in this case to build a refracting type telescope. Probably the most important part of the telescope is the lens. The quality of this component will largely determine how well the telescope performs. Probably the next most important component is the focuser. It holds the eyepiece or camera at the correct distance from the lens required to give a nice, sharp, focused image. It needs to be stable but smooth and easy to adjust. To get these two important components working well together, you need a rigid telescope tube to connect them. Adding baffles to the tube interior will help reduce internal reflections and improve contrast. A few other components I already have. For example, I have lots of eyepieces and cameras already. I also have lots of extension tubes in case I need to tune the telescope's back focus distance. The lens I also already have, but I will talk about that in a moment. All the other parts required to build a functioning telescope I did not have at the outset of this project, but that was quickly put to right by AliExpress and my local Home Depot, as you will soon see. Now let's get back to the discussion of telescope lenses. The simplest lens has a single glass element. It is the cheapest lens option and is readily available from numerous sources. Its main drawback is that it is prone to severe chromatic aberration, an inability to focus all of the colors of light to the same point in space. Chromatic aberration can be improved if we instead consider an achromatic doublet lens. These lenses are more expensive, but are still reasonably available. The use of two lens elements allows for a greatly reduced chromatic aberration. The best chromatic aberration performance comes from an apochromatic triplet lens. These are the most expensive lenses and are only available from a limited number of retailers. Their three-element design pretty much eliminates the problem of chromatic aberration. There are a number of retailers out there selling lenses, by the way, probably the cheapest being Surplus Shed in the US. They have lots of singlet element lens available as well as a number of achromats. You have to keep your eye on them as their stock changes regularly. I have often bought lenses to play with from that online store. For my telescope project, the lens, and in fact the whole impetus for building the scope, came from the ASCAR V. I purchased this refractor system in December of 2024 to be my grab-and-go scope, to be used at outreach events and when I am on summer vacation. The system comes with two triplet apo lenses, an 80mm and a 60mm aperture. It can be switched between 8 different optical configurations using the included focal reducer, field flattener, or teleextender. I have had very good success with the ASCAR V. It is super flexible, has good optical performance, and has a very high quality construction. After a few months of using it, however, I came to a very troubling question. What do I do with the second objective lens when it is not in use? The tinkerer half of my brain came to an obvious answer. Make a second telescope. Being an engineer by trade, the first thing I had to do was sketch up my plans to scale on the computer. I already knew what the lens I would be using was and had an idea of what plumbing components were available, so those were easy to sketch in. I also had recently purchased a solid 2-inch helical focuser from AliExpress, so I knew the dimensions of that component. That left me with two important missing parts: the lens adapter and the focuser adapter. A lot of searching online for pre-existing parts with the threads and overall dimensions I needed ended with me finding something that would work, again, on AliExpress. The lens adapter is in fact a focuser mounting adapter that just happens to have the correct M78 thread. The focus adapter also just happened to fit nicely into the outlet end of a 3-inch to 2-inch ABS reducing coupler. With the geometry of the scope sketched up, I was also able to figure out the dimensions and mounting locations of my baffles, 3 in total. From my drawing came a parts list. The lens, as I already mentioned, was one of the objectives from the Ask RV. The lens shade, or what some call a dew shield, was already integrated into the lens assembly, so that had also been covered. The lens cell adapter came from AliExpress at a cost of $50 Canadian. The telescope tube was made using scrap 3-inch Schedule 40 ABS pipe that I had laying around, plus a straight coupler that cost $3 at Home Depot. I cut the baffles out of the lids of empty yogurt containers, painted with flat black camouflage paint from Home Depot at $17 a can. The focus adapter was made from a $8 3-inch to 2-inch ABS reducing coupler and an M54 to M48 adapter from AliExpress at $14. The focuser was the most expensive component, other than the lens, at 128 Canadian from AliExpress. Finally, the miscellaneous 2-inch extension tubes I also got from AliExpress for $38. Thus, the total cost of procuring all of the parts was just under $260 Canadian. Step 1 of the build was to cut all the ABS components to the correct length and sand the edges square and smooth. All the couplers had to be turned on the lathe at my work in order to remove the slight taper on the inside. Otherwise, the 3-inch pipe would not seat all the way into the couplers as I had originally planned. I also drilled and tapped the aluminum lens adapter to receive the 1/4-20 screws that I would use to connect it to the ABS pipe. Metal shims were required to properly center the lens adapter on the pipe since it was very slightly larger than the pipe outer diameter. The loosely assembled components can be seen in the image on the right. Step 2 was to do a quick field test of my loosely assembled prototype. I did a daytime test using both an eyepiece and a camera, looking at a target very far away. I was successful reaching focus with both, confirming that my pipe lengths were all correct.
Is that one? I remember you said there was one that was dead.
We can hear that microphone, by the way, guys.
Oh, hang on.
Step 3 was to mask the subassemblies and apply flat black paint. All interior surfaces were painted. I was quite pleased with the resulting finish, as it was indeed a very flat and non-reflective surface when finished. At this stage, I also cut out my 3 baffles and painted them. Step 4 was to do the final assembly. I used standard ABS cement to connect all of the plumbing parts together. I did consider just bolting them together so that the telescope could be disassembled in the future if necessary. In the end, cementing was simply way less effort. The 3 baffles were held in place by being pinched between 2 adjoining plumbing parts. The M54 to M48 adapter is connected to the ABS reducer using epoxy. Again, I thought of using screws, but in the end, the epoxy was much easier. The last assembly step was to give the whole exterior a silvery metallic paint job, both to make it look nice and to reduce the heat load on it when I was using the scope for solar observing. Step 5 was to give the scope a final proper field test. I did this at a fall star party where I put it up against the ASCAR V proper. Mounting of the scope, by the way, was done using ADM brand rings and dovetail bar. Based on the results of my observation sessions that weekend, I am very happy with my project. My homemade scope delivered good contrast with no internal reflections and an easy-to-use, stable focus. In summary, this was a very fun project. It was easy to do and used readily available materials. The success of my project hinged heavily on finding a threaded adapter that fit the ASCAR objective lenses. So thank you, AliExpress. Now I have 2 Apple refractors at my disposal for nearly the price of 1. Thank you. If there are any questions, I'll be happy to answer them.
All right, I think. Oh, God. Now we're getting echo. Testing 1, 2.
Where are the earbuds? Where the
Now what? Is that okay?
Yep. Over
Okay.
the podium.
So people will have to wear the earbud when they come up?
I don't think just trust.
We're clearly being haunted by ghosts. Obviously a major malfunction. This is not going to wash. So we're trying to do a microphone from here to circumvent these guys, which don't seem to be working.
There's still a bit of an echo, but it's not as bad as before.
Oh, really? Okay. You're coming through nice and clear.
Speakers here, speak loudly.
Now that was an echo. I'm at a Pink Floyd concert.
Yeah, as Mick was saying, they're here. All right. Wow, man. It's just, can you kill the speakers? That might help. Okay, testing. Speak really loudly. I am. Louder? Are we go for launch? Yeah. Okay. All right, bear with us, folks. We're going to try to run through this. We're going to do our observation reports, and I'm going to ask you guys to come down here and speak into the mic, as it were. All right, Bob, you can be our guinea pig. I don't know if I need the earbuds. Do I need the? I don't need the earbuds.
Please have to speak really loudly because we don't have any amplification in here.
Okay, so this is the microphone, apparently.
Giant,
Yeah.
thing, yeah.
So speak loudly.
Okay. Well, fortunately, I have nothing important to say. Okay, you want to start that first slide, please? I can't. I have hearing aids. All right. Hello? 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 This is the most fun I've had in a long time. Hello? Okay, so I just keep going? Okay, when I'm imaging an unknown object, I like to look at another astronomer's image to see what the object actually looks like. This image was taken by Adam Block and shows clearly a very interesting object. Notice all the colors. Next slide. Next slide, Chris. Where the? Oh, there it is. Okay, this is my image of the same object. It doesn't look anything like what's in Adam's photo. What the hell is going on? Next image, please. The image isn't as complete a miss as I first assumed, but only makes up a tiny portion. That little box is my image. Okay, next slide, please. This is my image again. Clearly, my field of view is ridiculously small for this image. Eric LeMay told me that when he imaged this object, he used a 50-millimeter camera lens, and I used a 1400-millimeter telescope. Next slide, please. When we return to Adam Block's image, we can see that he also includes the globular cluster M4. Next slide, please. I figured that since I couldn't get the whole image, I would at least get M4. Next slide, please. This and the next two globular clusters are all challenge objects. Next slide. Next slide. Is
One more?
I think so. Yeah. I can't remember the last time I imaged 4 globular clusters in 1 month. Next slide. This beautiful nebula is best known as housing the pillars of creation. Next slide. Everything else that I imaged this month was low to the horizon and only above and between the trees for short periods of time. I decided to do something high and easy, and so I chose this nebula, this planetary nebula. It is well situated in the sky for imaging and is the easiest planetary image to image. I strongly suggest that you drag out your camera and telescope and give it a try. Thank you.
Thank you. Thank you, Bob. All right. Jim, long time no see.
Yeah, long time no see. Okay,
So this apparently is. So just hold it.
do I have to wear
You don't have to
earbuds?
worry about it. Just
Okay.
don't cover the microphone. And you
Look into my eyes. You're getting sleepy. Okay. So these are some challenging objects. The first one is the Jupiter-Venus conjunction. And this was taken on June 8th using the Sharp Star 94 millimeter refractor. And at that particular time, the two planets were approximately a little bit more than 1.5 degrees apart. And with focus, I was able to capture 3 of Jupiter's moons, Europa, Callisto, and Ganymede, from left to right. It was a very clear night. And so later that night, I decided to go for the next 2 challenge objects. This is M12, a globular cluster in Ophiuchus, 23,000 light years away, discovered by Charles Messier in 1764. This image required approximately 4 minutes of exposure using the Malincam DS 8300C Tech camera with a UHC filter. And the next one is M107, discovered by Pierre Méchain in 1782. And this is often referred to as a loose globular cluster because it's not as compact in the core. It's approximately 20,000 light years away and is one of the oldest globular clusters known to be between 12 and 13 billion years old. Thank you.
Thank you, Jim. All right, next up we have Rick Wagner.
Good evening, everybody. So I'm also a member of the Kingston Center, and one of the things we recently purchased for members' use in Kingston was the new C-Star 30 Pro. And by we're moving through the slides. By offering to document the thing and test it out for the membership, I was allowed to have it first. And one of the things I started testing was the plan function, which allows you to schedule a whole series of observations through the night. And unfortunately, I didn't have a chance to really use it before I had to give it back. But I thought this is a really cool function. Kim Hay in Kingston is trying to image all the Messier objects. And I thought, man, with that plan function. And about 3 days later, I thought, wait a minute, I've got a computerized telescope. All I have to do is do the plan. So I started the plan. And these are the images from one night of the globes. There's, was it 24 of them? So these are either 5 or 10-minute exposures with the Meade 10-inch Schmid Newtonian, and they're all luminance. They're all absolute minimal processing. And it just happens that at this time of year, if you want to image all the Messier objects, most of them are globulars. So there's some quite interesting ones. It's interesting to see that, like, some of them are quite small. M92 is really big, really nice, but it's so close to M13, nobody pays much attention to it. M19 is quite oval. Several of them have adjacent dark nebulae. A lot of them are way down south, scraping the horizon in Sagittarius. That's probably the smallest one I imaged. M71, some people think it's an open cluster, but and again, satellite trails, these are only 5 minutes, so there's only like 10 exposures at most. So satellite trails don't get eliminated very well. In processing them, M80 is right down next to Antares, where M4 was. So there's M92. You can see it's quite a decent size. These show up better on the computer. They're rather overexposed in the cores. And M107 is the last one, also has some of the dark nebulosity around it. So if you have a computerized scope, I figure if you've got a reasonably complete sky, 2 evenings separated by a few months, you could do the whole Messier list quite easily in 2 nights. That's it.
Thank you, Rick. That's quite the collection. All right. Jim, back to you.
All right, thanks, Paul. So this is my first capture from the Beach Bum Observatory this summer. This is from this past Sunday before all of the thunderstorms started to move in. It is a view of the sun in hydrogen alpha light, showing us all of the interesting details on the surface, like Jim shared with us in his talk earlier. This is with a new to me telescope. Up to this point, I have been filming H alpha with a 50mm aperture Etalon, and I recently upgraded to a dedicated 80mm aperture solar scope, double stack, made by Lunt, and I'm just getting to learn how to use it, and so far I am very, very happy with it. The fineness of the details that it's able to provide is pretty amazing. So this was the best 200 frames stacked out of a capture of 4,000. The seeing was really bad, so I captured a lot of frames and only stacked a small percentage. Stacked in a program called Auto Stackert. It's a free software. And then sharpened using IMPPG, another free software. And then I added a little bit of color to it, just in Photoshop. So yeah, so far so good at the Beach Bum Observatory. See you next month.
Jim, was there supposed to be another one? No? Okay.
Nope, just the one.
All right. Well, thank you very much. All right. And Richard Taylor.
Okay, well, thank you everybody for the pictures of all the challenge objects this month. This is quite wonderful. The constellation that we were looking at was Ophiuchus, which was rising in the east from FLO at the beginning of the month. So you can see the Milky Way along the eastern horizon there, a little bit hidden by the sky glow from Almont. Ophiuchus is a very big constellation. Sometimes it's a bit difficult to find all the pieces because they're so widely separated. So there's the actual pattern. It looks like a big child's drawing of a house. But if you look back at the previous picture, the thing that's easiest to see is the line of 3 or actually 4 stars along the base of Ophiuchus, and then a triangle at the top. So that's the general shape of it. Now, up at the top easterly corner, there's the summer beehive cluster, which was the level 2 challenge. And as I say, it's quite easy in binoculars. This picture with just a 16 millimeter lens on a DSLR could capture it definitely as a cluster of stars. So that's what the little inset is there. It's a full resolution portion of the picture. And that's the summer beehive with a telescope. And it's actually less impressive with the telescope because there are so many other stars of the Milky Way all around it. The beehive itself is a set of fairly bright stars, and they're all a kind of bluey white color, but there aren't very many of them. It's not a very dense cluster. And like the others you've just seen, I also tried to get all the 4 different challenge globular clusters, M10, M12, M14, and M107. But I did make a special effort this night in June at FLO to try and take all of the pictures using the same optics, the same exposures, and afterwards the same processing, so that you could see some of the differences between these globular clusters. And then, like Bob, I took a lot of different pictures of Rho Ophiuchus. This one I actually took when I was on my trip to New Zealand in March and April of this year, using a little portable C-Star 30. And surprisingly, the C-Star also has a fairly narrow field of view. So you just get this triplet of stars, which is Rho Ophiuchi, a bit of the blue nebulosity around it. And then you're starting to see some of the other colors off to the left-hand side there. But the area as a whole is huge. So this is now from FLO, start of June, but this is with a much bigger camera chip on a small refracting telescope. So now you're seeing some red and some orange on the left, as well as the 2 pieces that you just saw with the C-Star on the earlier picture. But it's even bigger. There's a much bigger field of view. This was taken from the Vantage Point Observatory in New Mexico. And it's actually a 2-panel mosaic with a ASI 6200 camera. So a very large chip. And as I say, two panels. And this is a total of about 20 hours of exposure through RGB filters on a monochrome camera. So you see that we've got the globular cluster M4 down there. There's Antares, the orange star in the orange nebula, and red and blue and dark nebulas all through it. It's a really, really wonderful area, and long exposures work so well at this picture. So those were the challenges, and you did see one picture of the Venus-Jupiter conjunction. And of course, we saw right at the beginning of the meeting the lovely emergence of Venus from behind the moon in Deborah Saravolo's daytime picture. Was the picture of the astronomy picture of the day. On the Discord server, Xavier also captured all of the globular clusters in the summer beehive. Mark Lilienthal and Rob McCallum had some other nice pictures of Venus, Jupiter, the moon. Oh, I made a typo there. It should be on Mercury as well. So I also managed one night to see Mercury very low on the horizon from the experimental farm. But it was, you know, so close to the sun, it was very difficult to get dark enough before it would just fade out and go below the horizon. So for this coming month, you probably expected me to do the sequence here. We had Serpens Kaput, we had Ophiuchus, the serpent bearer. So it would have been logical to have Serpens Cauda as the challenge constellation for this month. But it doesn't have very much in it. So taking advantage of the summer Milky Way, I thought it would be better to have as our challenge constellation for this month, Aquila, the eagle, which is right across the summer Milky Way, and it's just full of lovely, lovely objects. So it was a bit of a challenge to come up with just a few objects for this month. So for level 2 binocular challenge, we have NGC 6709, and Stellarium calls this the flying unicorn cluster. It's quite a small cluster. It may be just a little tiny fuzzy patch in binoculars, but I did get a glimpse of it in my Seastar last night, and it came out quite nicely, and it actually does look a little bit like one of my granddaughter's stuffies, a unicorn. So take a look, see if you can see the shape, or use a lot of imagination. For the third level challenge, I thought we'd bring in something a bit more unusual, another dark nebula. E. Barnard was an astronomer in the latter part of the 1800s and the early 1900s, and he really explored a lot of different dark nebulae, and he cataloged them. So if you see a catalog number starting with B, it's for Barnard's catalog. But E. Barnard has a section just in the corner of Aquila, near the tail of Aquila, where there's actually a dark nebula in the shape of an E. He cataloged it as two different portions. The lower bar is, look at my notes here. B143, B143, and the upper part is B142. But if you look at it, or if you take a picture of it, I think you'll see it looks very much like the capital letter E. It's quite large. It doesn't need a lot of magnification, but it does require pretty dark skies. And then Aquila also contains quite a number of planetary nebula. I've never seen these before, so I'm going to have a challenge myself in trying to find these. They're pretty small. They're only about 3 or 4 arc minutes across. So you'll need a high magnification, a large aperture in order to capture these, but they're quite beautiful and not too dim. So you can sort of use a fairly short exposure on these. Now, for the solar system challenge, it just happens that the asteroid Juno is traveling through Aquila right now, and it's at its opposition on July 9th. Not a very favorable opposition. it will only get up as bright as about magnitude 9. And because it's so close to the Milky Way, it's going to be a little bit difficult to spot. But if you take pictures on multiple nights, or if you keep careful track of the stars in the area, you should be able to see it moving from night to night. And that's the way to tell it that you've caught the asteroid. I've drawn the path on the picture here at the start of July at the tail of the arrow, the end of July at the point of the arrow. So those are your challenges for this month. And don't forget my other challenge. Please, we need more volunteers to help out. We're going to have an election in December where a lot of members of the executive are going to be changing over. So please think about contributing to the Ottawa Centre by volunteering to help. Thank you.
All right, public star parties. Our next one is on July the 17th, and this is obviously as a public star party. It'll be at the Carp Diefenbunker site. And our rain dates are the 18th, the 24th, and the 25th. What, us get rain? Go figure. And again, timing is from basically from 8 o'clock till 10:30. Or obviously, as long as we have clear skies there. And if you want further information there, you can just have a peek at the URL at the bottom of the screen. And as Richard mentioned, we're always looking for volunteers. So if you're in the headspace to come out, bring your equipment and enjoy the party. If you need any more information at all, feel free to call Deepinder. He's our Star Parties coordinator, and he's more than willing to hear from you. All right, Canada Day. We want to thank the folks on the list here: Xavier, Dave, Ron, Cliff, Paul, and Chris for their efforts. We did have a somewhat successful Canada Day there, and before the skies opened up on us there, so and some good turnout with telescopes to show people what there was to see. So thanks again to those folks that made that possible. A couple of images there. And oops. There are Fred Lossing Observatory star parties. These are for our members only. And the next one is on July the 11th. We have a waning crescent moon. So hopefully we'll get some decent skies. We'll cross our fingers. And if you need any club information, those are the folks that you want to contact. And thank you all for coming out. We had 69 members today, which is, or 69 years today. Hope you all didn't mind the major malfunction that we had. We'll hopefully have that rectified for our next meeting. If you have any comments at all, especially if they're positive comments, feel free to contact me. Otherwise, yeah, I'll hear from both positive and negative. Yeah, negative comments to you just volunteered. Negative comments to Dave, positive to me. Thanks, Dave. All right, and then our next meeting is on Friday, August the 7th. We'll have our problems sorted out, I'm sure, by then, 7:30. And again, observations and ideas to me. I'm going to send I usually send out, well, I always send out my monthly meeting announcement about a week or so before the meeting, just as a reminder. I'm going to send out another notice there. We've been doing some restructuring of how we're doing our presentations and our observations. So stay tuned for that, watch for that. It's just a guide for folks that want to put together presentations. We're trying to tighten up our meeting timing a bit. So I'll send that out probably in the next week or week and a half. So thank you for coming. For those that are interested, we have our post-meeting entertainment at Liam McGuire's down on 1705 Saint Laurent. And again, I wish you belated Happy Canada Day, and be careful on the way home tonight because there's clearly a major disruption in the force. All right. So take care. All right. We'll see you all next month. Thanks for coming.